Hello viewers, welcome back to this channel. So mainly in this channel we always cover chemistry alongside mathematics for advanced level based for senior 5 and senior 6. So in this video we are going to look at U.A.C.E Inorganic Chemistry, and we are going to be covering a topic known as period 3 elements. Now, period 3 elements should be one of the first topics covered in inorganic chemistry. Reason being, it combines all the knowledge of other groups. So pay attention as you are going through this topic and make sure that you refer to other videos in case you don't understand some of the concepts I may skip in this lecture. So this video is presented to you by Yusuf, and you are advised to subscribe to the channel just in case you don't miss out any updates. So you are saying that pure 3 elements run from sodium to argon, and when you get your periodic table, period 3 is the third row on your periodic table. And we are saying that we have given some of the table here showing physical properties of period 3 elements. In other words, these are the same properties that happen across the period. So we only pick one period, which is period 3, to represent all other periods. Now, for advanced level chemistry, U.A.C.E certificate, the only period you are supposed to cover is period 3. Now, starting on the table, we have the melting point. Now, in our previous videos, we all talked about what affects the melting point. Explanation of melting point, first of all, you have to understand the structure of each element. And then after understanding the structure of each element, you have to talk about the forces holding the structure. Now, if you're having more than one element with a specific structure, what varies their melting point will always be the bond length. And if bond length isn't valid for the explanation, that's when we refer to individual elemental structures. So we are saying that for melting point, it increases from sodium to silicon, and then it decreases, it again increases from phosphorus to chlorine. I think this is a decrease. Electronegativity, as we explained all these things in periodicity, which was the first video on this channel. So if you didn't watch that video, you are advised to go back and review the video before you approach this lesson or lecture. So all this is periodicity, and periodicity was explained in the first video which was uploaded on this channel, and that video we named it periodicity. So we are going to look at each one by one, and we are saying that melting point is a constant temperature. Now here, this word is key, and we shall put here half a mark in case we ask you for the definition. It's always a constant temperature at which a solid changes to a liquid. But take note that this is a physical chemistry definition, and physical chemistry definition we always expect a condition, and the condition here is going to be constant pressure. So you are saying that melting point increases from sodium to aluminium. And why is that the case? And we are saying that this is because from sodium to aluminium, the strength of the metallic bond increases due to increasing the number of electrons contributed for metallic bonding. Now, towards the end of the periodicity lesson, which was uploaded on this channel, I gave the reason for this. I said metals have strong electrostatic forces of attraction, and their structures are held by metallic bonds. And those metallic bonds, their strength depends on either atomic radius or number of electrons contributed for metallic bonding. If you look at sodium, sodium only contributes one electron for metallic bonding. So sodium is going to form the weakest bonds, which require a low amount of energy to be broken. Whereas magnesium only contributes 2 electrons for metallic bonding. That means that melting point of magnesium is going to be slightly higher than that of sodium. And similar applies to aluminium. The higher the number of electrons contributed by each metal for metallic bonding, the stronger the metallic bonds. And the stronger the metallic bonds, that means that energy required to break those bonds is going to be higher or progressively decreasing. So similarly, aluminium is going to have a higher melting point than magnesium, which is also for the same reason. So there are two reasons why melting points keep on increasing. This is due to one of them is due to increase in the number of electrons contributed by each metal for metallic bonding, so that metallic bonds become stronger. And the other reason is because atomic radius is going to be decreasing from sodium to aluminium. That means that bonds are going to be shorter. And in the previous video, I said the shorter the bonds, the stronger they are. And the stronger they are, that means that more energy is required to break such bonds. That means that the shorter the bond, the stronger it is, the more energy required, and the higher the melting point. So let's go to another slide. So in this slide, you are proceeding with the explanation that I've just given. So you are saying that melting point is also increasing due to a decrease in atomic radius, because a decrease in atomic radius will cause the bond length to be shorter progressively from sodium to aluminium. The shorter the bonds, the more stronger they become. That means that the more energy will be required to break such bonds. And once more energy is required to break such bonds, that means that melting point is going to be higher. Now we are saying that aluminium has a slightly higher melting point than magnesium. And why is it slightly higher? Why isn't it very high? And you are saying that it's slightly higher because aluminium doesn't contribute all its electrons for metallic bonding. That means that aluminium, it would have contributed 3 electrons for metallic bonding, but it doesn't contribute all these 3 electrons, implying that in aluminium, melting point will be slightly than that of magnesium, just slightly higher. And the reason for that is because aluminium as an atom does not contribute all its electrons for metallic bonding. Proceeding with the explanations, we are saying that there is a drastic increase in melting point from aluminium to silicon. And why is it the case? Now, aluminium is a metal and silicon is a non-metal. But we are saying that silicon has giant combined structure. See, we are going to look more at this in group 4. Silicon has a giant combined structure, and in that giant combined structure, it forms strong covalent bonds, which is here. So you underline this or highlight it in your notes. What you want to see is this, and that's where we shall put a half a mark. So silicon has a giant covalent structure, and giant covalent structure is held by strong covalent bonds. And once the covalent bonds are stronger, that means that energy required to break them is going to be very high. And once energy required to break them is very high, that means that also melting point is going to be very high. Now we are grouping all other remaining elements, reason being they all have the same structure. Now if you look at phosphorus, sulfur and chlorine, all of these ones are having simple molecular structures. That's why it was highlighted and bolded. simple molecular structures, and simple molecular structures are held by which forces? You'll find that simple molecular structures are always held by weak van der Waals forces of attraction. And just like in the previous video, we have been repeating this because inorganic chemistry is repeating. So van der Waals forces of attraction, their strength or magnitude, we say that it depends on the molecular size or molecular mass of a given element. That means that the higher the molecular mass or the higher the molecular weight of an element, the stronger the van der Waals forces of attraction holding its structure. That means that to break such forces, more energy will be required. Now on phosphorus, sulfur and chlorine, we ask ourselves which one will have the higher molecular mass. So if you look at all of them independently, sulfur is octatomic. Octa means 8. That's why I said, because sulfur exists as an S8. This one means sulfur is octaatomic, is an octaatomic molecule, which implies that being octaatomic, it is going to possess a higher molecular mass. And since the strength of the van der Waals forces depends on molecular mass, that means that it's going to have the strongest van der Waals forces of attraction in it. And once they are stronger, that means that energy required to break them is going to be high, making sulfur having the highest melting point. Now sulfur has a melting point which is greater than phosphorus. Reason being, phosphorus is tetraatomic, represented by P4. That means that phosphorus is having a slightly lower molecular mass than sulfur, and its forces are going to be lower. These van der Waals forces of attraction are going to be weaker than those ones in sulfur. Hence, it is going to have a lower melting point than sulfur. So I hope that explains these two. Chlorine exists as a diatomic molecule. That means that it has the lowest molecular mass. And once it has the lowest molecular mass, that means that it's going to have the weakest van der Waals forces of attraction. Hence, it's going to require little amount of energy to be broken. As a result, chlorine will exist as a gas at ordinary temperature because the forces are very weak. And once they are very weak, that means that room temperature is enough to break the van der Waals forces of attraction holding its structure. That means that it can easily exist as a gas, because in gaseous state, atoms are spread from each other. That means that forces holding them are very weak. Now in this slide, you are going to look at some of the reactions undergone by period 3 elements. Now these ones are simple. All you need to master is the oxidation state. Like I said, period 3 as a group combines most of other periods. The only thing that we won't cover in other periods may be phosphorus and sulfur. Others, you are going to cover them individually. Sodium, you are going to look at it in group 1 or group 2. Similar applies to magnesium. And aluminium is handled as a single topic, which is the next video to be uploaded. So each and every element when heated. Now most students forget this and they lose marks. They start saying that inorganic chemistry is difficult. Inorganic chemistry is principled. We expect that a reaction can't take place unless conditions are available. So if you miss out the conditions, you are always denied marks. So yeah, that's why we are saying all elements when heated react with oxygen. And the only exception that we gave was chlorine. In the group 7 video that was uploaded on this channel, we say that chlorine forms three oxides. There's chlorine 7 oxide, there's chlorine 3 oxide, and there's chlorine 1 oxide. But all those oxides are not prepared by direct preparation with air. So the condition was heating. All elements, when they are heated, they are going to react with oxygen and they are going to form oxides. And here are the equations. Now this is phosphorus trioxide. Phosphorus trioxide is written like this, or someone else can reduce these numbers and write it as P2O3. Or this is phosphorus pentaoxide or phosphorus 5 oxide. Someone can reduce the numbers and write it as P2O5. So the oxide of sodium is this, and this is when excess oxygen is provided. However, in limited oxygen, sodium will form sodium oxide. Proceeding to the reactions of hydrogen. Now we are saying that sodium and magnesium when heated reacts vigorously with hydrogen to form ionic hydrides. And we are saying, now note that all the conditions that are required are bolded, implying that if you're trying out an inorganic number and you don't consider the things that are bold, you are most likely to lose marks. So we are saying that heated sodium or magnesium will react vigorously with dry hydrogen gas to form ionic hydrides. And we are saying that we are forming ionic hydrides because we are reacting a metal with a non-metal. Usually we form ionic compounds. That's why we give these equations. Sodium and magnesium reacting with magnesium will form the respective hydrides. Writing each of these equations will carry 1.5 a mark, provided the states are well written and the equation is well balanced. However, in A level, when you write an unbalanced equation, no mark is awarded to such an equation. So we are saying that note, since these ones are ionic hydrides, when you mix them in water, we always get a metal hydroxide. And we shall always observe a colorless gas that will burn with a pop sound, and that's always hydrogen gas. So take note of these reactions, and when you're reading, make sure you don't ignore these notes. Now, some teachers ignore the notes of PO3 elements reacting with hydrogen, but if you look at the mock bodies, like most students ignore to read the mock papers. If you look at the mock bodies, they are bringing back such questions, so implying that you should read them without fail. Now we are saying that aluminium, silicon, and phosphorus do not completely react with hydrogen gas. When you are answering inorganic chemistry, you are always awarded marks in the bracket. I've told you each of these equations is going to carry 1.5 a mark. So always look at the mark allocation that has been given. Like when you open a question bank, you look in the mark allocation. The marks that have been given aside will help you determine how far you should read, how far you should write. And this statement of exception or abnormalities is always given 1 full mark. So as you're writing, make sure that as you're reading, make sure that you take note of such statements, and it's advisable to start with them as you're answering a question about period 3 elements. And then you are saying that chlorine and sulfur is going to react with hydrogen. Chlorine reacts in presence of sunlight or ultraviolet light. Now note that in A-level chemistry, especially in organic chemistry, you cannot tell us that things are going to react without telling us the conditions that are required. That's why we are saying that chlorine is going to react in presence of sunlight or ultraviolet light, and they are all going to react to form their respective hydrides. Chlorine is going to react with hydrogen gas to form hydrogen chloride gas, and sulfur is going to react with hydrogen to form hydrogen sulfide gas. Both of these ones are acidic gases, implying that they can be dissolved in solution to form acidic solutions, or they can be dissolved in water to form acidic solutions. That's why we are giving a continuation that The chlorides react with water to form acidic solutions. Now these are ionic equations implying that they just ionize in solution. When these ones ionize, they are going to release protons. Now the protons react with this water. Hydrogen ion react with this water. That's why we form an hydroxonium ion. This is called an hydroxonium ion. Similar applies to hydrogen sulfide. Hydrogen sulfide in solution is going to release protons or hydrogen ions. So hydrogen ions are going to come and react with this water. And after that, this water will give us hydroxonium ion. So this ion is called hydroxonium. If you feel like you forget it, find a notebook and you note it. It's called hydroxonium ion. So going away from that, we are going to look at the reactions of elements individually, and we are going to start with reactions with water. So I missed here a subheading. You can add it if you have taken these notes. You can say part A with water. And we are saying that sodium reacts with water vigorously. Now this is a commonly set question in UNEB or in other examination bodies examining period 3 elements. It's a very commonly set question examining period 3 elements. Now you should take note that it's only sodium that reacts with water, and you are going to find that all other elements are going to be reacting in form of steam. So it's only sodium in period 3 that's going to react with water. Magnesium just slightly reacts with water, but we don't consider that reaction. The only vigorous reaction magnesium has with water is when water is in form of steam, as applied here. So you are saying that sodium is the only metal that reacts vigorously with cold water to form sodium hydroxide and hydrogen gas, as stated in the equation. And now you're saying magnesium reacts slowly with cold water, but it's going to react vigorously with steam. And this is the only equation that we need. But if you feel like you may be awarded an additional mark for writing this statement, you may get half a mark. But the major equation which is required is you telling us that magnesium reacts vigorously with steam on heating. I told you conditions are key in chemistry, so always don't forget to write conditions. The condition here was heating. So you're saying that on heating to form magnesium oxide and hydrogen. That's why when you're heating magnesium in its solid state, reacting it with steam. Hope you are recognizing these states. So magnesium is reacting with steam, and it's reacting with steam to form magnesium oxide and hydrogen. Now notice that whenever we react anything with steam, we always form an oxide, but whenever we react anything with water, we form an hydroxide. Take note of that. So magnesium will always react with steam to form magnesium oxide, and the other product is going to remain the same, which is always hydrogen gas. Now all other elements are going to react in the same way. So you're saying that aluminium is also going to react with steam on heating. I said conditions are very important. Without writing conditions, you are not awarded any marks. So aluminium is going to react with steam on heating to form aluminium oxide and hydrogen. Like I've told you, if you're reacting water in form of steam, the only product you always get is an oxide. But if you're reacting water when it's cold or when it's in liquid form, you are going to get an hydroxide. Take note about that. Then the other product is going to remain the same, which is hydrogen gas. And then lastly, silicon and phosphorus react with steam. When heated, conditions are very important. You are going to lose marks. Your equation will be denied to be marked if you don't write conditions, because we believe that without conditions, that's not chemistry. So silicon forms silicon dioxide and hydrogen gas. That's why the equation is being formed. Like I said, we are reacting it with steam here. That's why we are giving an oxide. So let's proceed to the next slide. In this slide, we are saying that phosphorus and sulfur do not react with water at any condition. Phosphorus and sulfur do not react with water at any condition. I want you to take note of that. I don't know, I remember in the last video I talked about 8 of this in the last slide, but this is the valid thing. So edit your notes and say phosphorus and sulfur do not react with water at any condition. So this, as I said earlier, this is marked. At any condition, the statement at any condition means that whether water is in steam form or cold state. That's the meaning of this statement. Phosphorus and sulfur do not react with water at any condition. Now we are saying that chlorine reacts with water. Now, I've given the reactions of chlorine individually in group 7, and that video has also been uploaded on this channel. So either way, it's either you start with this video and you go back to the other video, or you can start with the other video and you come back to this video. So I said that chlorine, when it's reacted with water, it undergoes disproportionation. So it will be forming hypochloric acid and hydrochloric acid. And some people say hypochlorous acid and hydrochloric acid. Now there is an alternative name for this, so you should pick the one which you are well conversant with. But chlorine, like as in covered in group 7, chlorine reacts with the same way like bromine and iodine. So both of the three, they give us hypohalic acids and hypohalous acids. So hope you have already seen that video and got conversant with the explanations. So looking at reactions of chlorine, like I've talked about chlorine in group 7, that's why I first posted that video. We say that chlorine is an oxidizing gas. So chlorine always oxidizes elements to their most stable oxidation state. Not most, but top stable oxidation states. So chlorine, when reacted with sodium, we shall form chlorides, and these are going to be ionic chlorides. I told you when you react a metal with a non-metal, we always form ionic compounds. Let me hope you are aware about that. So aluminium forms a covalent chloride. Now why does aluminium form a covalent chloride? Now we expect that you have already got some knowledge about polarization. Aluminium has a charge density of 3 plus, positive 3. That's the charge on the aluminium ion. So this charge is very high. It's going to cause a very high charge density around the aluminium ion. That means that the aluminium ion is going to greatly polarize the anion which is married to. So once aluminium is in ionic bond with the chloride ion, this high charge density is going to highly polarize the chloride ion. And once it's highly polarized, that means that the whole compound is going to turn the tendency from being ionic to being predominantly covalent. So it's due to high charge density that causes high polarization power of the anion, which is chloride ion, making the whole compound predominantly covalent instead of purely ionic. And as we know, covalent compounds are going to be easy to break, so we expect the melting point of aluminum chloride to be lower. Reason being is it's predominantly covalent, and also that question is commonly asked. So we are saying that aluminum chloride dimerizes in vapor phase, and that's due to its high polarization power. It dimerizes to a polymer, and this polymer has a structure, so we shall look at it in the videos of physical chemistry. So going to the next point, we are saying that silicon, phosphorus, sulfur also react with chlorine on heating to form covalent chlorides. Now the reason why we are saying that covalent chlorides are being formed here, this is because we are reacting nonmetals. When you are reacting two nonmetals, we expect formation of covalent compounds. And covalent compounds, that means that they are going to have simple molecular structures. And I told you, when they ask you melting point about compounds with simple molecular structures, their melting points always increase with increase in the strength of van der Waals forces of attraction. And van der Waals forces of attraction, in turn, their strength depends on the molecular size or molecular weight of the substance. So silicon reacting with chlorine will form silicon chloride. And in group 7 video, I shown you how we can get silicon chloride, because silicon is a group 4 element. Group 4 elements have two oxidation states. They have the +2 and the +4. So when we react chlorine directly with silicon, we get the most stable, which is the +4, because silicon is a very oxidizing gas. So to prepare silicon chloride, we always use hydrogen chloride, like it was explained in group 7 video. That video is already uploaded on the channel. After watching this, make sure that you approach it and you rate its notes too. So other elements are going to react to their topmost stable oxidation states. So phosphorus is going to react with chlorine to form phosphorus 5 chloride. Now this is the most acceptable equation. This one may be in limited chlorine, but this is very rare. So I advise you to eliminate this one, because chlorine is a very oxidizing gas. So you expect chlorine to be reacting with phosphorus to oxidize it to the +5 oxidation state. That means that we are going to form phosphorus pentachloride. Now this is a commonly asked question in UNEB. When sulfur reacts with, in fact, you should put a mark on this. Make sure that you master this equation before you go for your papers, because we highly ask this question. When sulfur as a liquid is reacted with chlorine as a gas, we form disulfide dichloride, and this is a yellow liquid. Take note about the states. We heat sulfur in its liquid form, and we react it with chlorine in its gaseous form to form disulfur dichloride in a liquid form. So be aware of this equation, because we highly ask it. Now let's look at some of the reactions period 3 elements have with acids. Now in these reactions, some of them I missed out reactions of magnesium, but I think so. I'll be talking about where I missed out, and for those of you who are taking notes, I always advise you to first pause the video and take the notes and then proceed with the explanation. So you're saying that sodium, magnesium, and aluminium react with dilute acids, and the reason for that is because these ones are metals. Metals always react with acids in whichever condition to form respective salts and hydrogen gas. So sodium will react with dilute hydrochloric acid to form sodium chloride and hydrogen. Similar applies to magnesium. Magnesium will form magnesium chloride and hydrogen. Sodium will react with sulfuric acid, dilute sulfuric acid to form sodium sulfate and hydrogen. So take note of this. Now, sodium on this reaction is only valid with concentrated with dilute called dilute sulfuric acid. Otherwise, with concentrated sulfuric acid, we always form sodium hydrogen sulfate. This reaction is only valid with dilute sulfuric acid. That's why this is the same reaction we give you in your practicals. Whenever you're reacting any element with sulfuric acid, like sodium carbonate, we expect it to form sodium sulfate. So take note of that. So proceeding, we are saying that concentrated sulfuric acid oxidizes elements magnesium and aluminium to their respective sulfates, and the acid is reduced to sulfur dioxide and water. Now, whenever you are dealing with an equation involving oxidation, it's always advisable to write it in this format. Now, the condition here was concentrated sulfuric acid, because we don't believe that dilute sulfuric acid oxidizes. So it's always concentrated acids that oxidize. Always concentrated acids that oxidize. That's why we are saying concentrated sulfuric acid oxidizes magnesium and aluminium to their respective sulfates, and the acid itself is reduced to sulfur dioxide and water. I said these are called redox reactions, and redox reactions are going to be covered this week, or the videos are going to be uploaded talking about redox reactions. So every explanation for this video and for balancing of this video of such equations is going to be uploaded in that video. But for now, you can take the notes. So proceeding, we are saying that nitric acid. Let's look at nitric acid. So we are saying that sulfur reacts with concentrated nitric acid forming sulfuric acid, nitrogen dioxide, and water. So sulfur is nitric acid. It's always this concentrated. Whenever you're seeing that an acid is concentrated, that means that it's going to oxidize. So the appropriate way to read this statement was concentrated nitric acid oxidizes sulfur to sulfuric acid. So sulfur is oxidized to sulfuric acid, and the acid itself, which is nitric acid, is reduced to nitrogen dioxide gas and water. So take note of that. That's how we write chemistry. Concentrated nitric acid oxidizes sulfur to sulfuric acid, and the acid itself is reduced to nitrogen dioxide and water. So proceeding, we are saying that phosphorus reacts with concentrated nitric acid, forming phosphoric acid, nitrogen dioxide gas, and water. Like as I said, anything concentrated, we need to say term of oxidizing. So the appropriate chemical way of writing this statement was, however, this is correct. This is correct. When you're writing it, you'll get a mark for it. But the more chemical way to present it was, concentrated nitric acid oxidizes phosphorus to phosphoric acid. Concentrated nitric acid, which is this one, oxidizes this phosphorus. So phosphorus is oxidized to what? Phosphorus is oxidized to phosphoric acid. And then the acid itself is reduced to nitrogen dioxide and is reduced to water. That's how we write chemistry. So the statement for this equation is concentrated nitric acid oxidizes phosphorus to phosphoric acid, and the acid itself is reduced to nitrogen dioxide and water. So we are saying that silicon and chlorine do not react with concentrated nitric acid. Like in group 4, we say that silicon only reacts with concentrated hydrofluoric acid. It does not react with any other acid. And similar applies to chlorine. Chlorine is not reactable to any other acid, and it does not react with any acid. So proceeding to the next acid, we shall have sulfuric acid. And sulfuric acid, we have already looked at it in dilute state. So let's look at it in concentrated state. I've said whenever something is concentrated, it's always going to be oxidizing. So we expect concentrated sulfuric acid to oxidize aluminium, and aluminium is going to be oxidized to its respective sulfate. And after oxidizing, what happens to the acid? The acid is reduced to sulfur dioxide and water. That's how we read them. Like we are going to be seeing how we are going to learn how to balance all these equations in the video I'm next to upload for the redox reactions. Now proceeding to the next slide, we are seeing that aluminium is oxidized by hot concentrated sulfuric acid to aluminium sulfate, and we say after the acid oxidizing, it gets reduced to sulfur dioxide and water, just like you are seeing. And similar applies to phosphorus. Phosphorus is oxidized by hot concentrated sulfuric acid to phosphorus pentaoxide. Now notice that this reaction is very different from that of nitric acid. For nitric acid, we form phosphoric acid, but for sulfuric acid, we form phosphorus pentaoxide. And after the acid oxidizing, it always gets reduced to the same reagents, which is always sulfur dioxide and water. So be aware of this compound. We don't form phosphoric acid with concentrated sulfuric acid. Rather, we form phosphorus pentaoxide. So let it not be tricky to you. So proceeding, sulfur is oxidized by hot concentrated sulfuric acid too. But sulfur is always going to be oxidized to sulfur dioxide gas, and the only product that will be left will be water. Reason being, we don't have enough elements in the equation. So let's proceed to reactions of the elements with alkalis. Now notice that sodium and magnesium are not going to react with the alkalis. And the alkalis here we are going to be using in most cases is going to be sodium hydroxide or potassium hydroxide. But preferably, U.A.C.E chemistry is now monoid to sodium hydroxide because it's the one that is abundant in large scale on the laboratory. So sodium and magnesium are not going to react with sodium hydroxide, and the reason for that is because sodium and magnesium are basic. They are bases, so we don't expect a base to react with a base. That's why we are saying sodium and magnesium do not react with sodium hydroxide at any condition. However, aluminium is going to react with hot concentrated sodium hydroxide or hot concentrated alkalis. We just need alkalis always represented by an hydroxide ion. So student who writes an ionic equation is better. But here I didn't use ionic equations. Ionic equations, we are going to use them in learning how to balance these equations, like it's going to be uploaded in the next video. The equations are very many, and you can't say that you are going to be knowing how to balance each of them without a specific formula. So we are saying that aluminium reacts with sodium hydroxide in presence of water to form sodium aluminate plus hydrogen gas. Phosphorus. Now here, this reaction for phosphorus, you should note it down. This is a very common reaction that we ask for and that many students fail. So phosphorus reacts with sodium hydroxide in presence of water to form what? We always form phosphine gas. This is called phosphine gas. And the other product is called sodium dihydrogen phosphate. So take note of this equation and always label it, so that whenever you are reading this heading, you consider it first. So silicon, as we said in group 4, is always going to react with sodium hydroxide in presence of water to form sodium silicate, and the other product will be hydrogen gas. sulfur is going to react with sodium hydroxide, form sodium sulfate. But it undergoes a disproportionation reaction, so it's going to form both a sulfite ion and a sulfide ion, implying that sulfur disproportionates in sodium hydroxide. Now you are hearing me talking about disproportionation. Disproportionation reaction is a reaction in which a single element undergoes oxidation and reduction simultaneously. So in this reaction, you are seeing that sulfur here in the first case is oxidized to a sulfate, and in the second case is reduced to a sulfide. That's what we call a disproportionation reaction. Now in this slide, you are being provided with a table showing you the boiling point, melting point. I told you boiling point and melting point are explained in the same way. We are looking at the bond. The bonds we have in chemistry for compounds, they are either ionic or covalent. So whenever I ask you for bond, don't state any other type. We always want either ionic or covalent for as long as it's a compound. Then the structure is always going to help you to explain melting points. And since from aluminum chloride and chlorine, they have simple molecular structures, then what we want you to explain to us, what we want you to reason out is that their melting or boiling points are going to be depending on their molecular size, because the molecular size is going to determine the magnitude or strength of the van der Waals forces. And once van der Waals forces are much stronger, we expect melting point to be higher. That's why you are seeing phosphorus pentachloride with the largest molecular size, it's having the highest melting point, followed by disilicon dichloride because it's the one which has the next lower molecular weight, implying that its van der Waals forces of attraction are slightly weaker than those ones in phosphorus pentachloride. So I prompt you to sit down in your groups and you discuss the change in melting point. Now in metals, the chlorides in metals, like we talked about aluminium chloride. We said aluminium chloride is having a very low melting point, yet we expect it to be ionic. That the reason we say it behind that, once again, we say that in aluminium chloride, the aluminium ion has a high charge density, and we say that charge density is 3+. So that high charge density is going to greatly polarize the chloride ion. And once the chloride ion is polarized, that means that the whole compound is going to be predominantly covalent, or it's going to be slightly ionic. And once it's predominantly covalent, that means that the forces that are going to be required to break the bonds are going to be low, causing a low melting or boiling point. We explain melting and boiling point the same way because of them are in line of bond breaking. So let's look at the preparations of chlorides of group 7 elements. We are saying that to prepare group 7 elements, you can either use chlorine gas or hydrogen chloride gas. So heating sodium with chlorine will form sodium chloride. Heating sodium with hydrogen chloride will form sodium chloride with hydrogen gas. Always make sure that your equation is balanced. Similar applies to magnesium. The same thing happens. And you're saying that magnesium chloride is ionic and dissolves in water. Since it's ionic and dissolving in water, we expect it to form an acidic solution. Now the acidic solution is because due to formation of hydrogen chloride. Hydrogen chloride dissolves in water to form hydrochloric acid, and in solution, hydrochloric acid ionizes. On ionizing, hydrochloric acid releases protons in solution. The protons in solution are responsible to make the solution acidic. Now this compound here is always given in your practicals. You're always going to find it in your practicals, qualitative chemistry. And we are saying that it is prepared by reacting magnesium or magnesium oxide or magnesium carbonate with dilute hydrochloric acid followed by crystallization. Let me hope you looked at that in O level. So let's proceed to the next slide. So sit down and you discuss this table with your friends. Make sure that you discuss all these periodic properties with your friends. Now this aluminium, we could divide this column and say that aluminium is having a predominantly ionic structure. It's not fully ionic because aluminium ion is having a high charge density. Hence that high charge density is causing a great polarizing power to the chloride ion attached to it, weakening the ionic bonds and making the whole compound predominantly covalent, making aluminum chloride having lower melting or boiling points. So in this slide, we are looking at how halides of magnesium are prepared. Magnesium can also be prepared by heating it with hydrogen chloride. Now this take note that this one must be, this is an acid. So once you react with magnesium chloride, magnesium as an element with dilute hydrochloric acid, we form magnesium chloride with its respective hydrogen gas. Let me hope you looked at all these reactions in group 2 elements. If you didn't, that video is going to be uploaded on this channel. Make sure that you go back and review all the reactions with group 2 elements and their compounds have with acids. So proceeding to the chloride of aluminium. How is the chloride of aluminium prepared? Still, it's in two ways. You can prepare the chloride of aluminium by heating. I told you conditions are very important in chemistry. So preparing chloride of aluminium, we say that we shall heat aluminium. That's why we are saying heating aluminium. Whenever you are heating, the gas is always going to be dry. Whenever you are heating, the gas is always going to be dry. That's why we are saying that heated aluminium is going to react with chlorine from its respective chlorine. And if it reacts with hydrogen chloride, we shall form the same product, which is aluminium chloride, but we shall be left with hydrogen. So that's why we add hydrogen on this side. Like we are going to see how we can balance equations. Make sure that you subscribe and you wait for that video showing you that how to balance most of the inorganic chemistry equations. So proceeding, we shall have silicon tetrachloride, and we are saying that silicon tetrachloride is prepared by reacting hot silicon with dry chlorine gas. All tetrachlorides of group 4, we said they have covalent chlorides. They have simple molecular structures. So, I told you how to explain the melting points of compounds with simple molecular structures. So we are saying that silicon reacts with chlorine, and chlorine is going to oxidize this silicon to its topmost oxidation state. That's why we are saying that silicon as a solid reacts with chlorine as a gas. On heating, there must be heating required. That's why I was bolding the condition. I said hot silicon will react with dry. The reason I'm saying dry is because when you're heating, we expect the gas to be dry. So hot silicon reacts with dry chlorine gas to form silicon tetrachloride, and this is a covalent liquid. Like we looked in group 4, all tetrachlorides of group 4 elements are covalent in nature, and they have simple molecular structures. So on proceeding, let's look at disulfur dichloride. So you're saying that disulfur dichloride is prepared by heating sulfur with chlorine gas. And when you heat sulfur with chlorine gas, you form a covalent liquid. So this is the only product, or this is the... We usually ask this equation, by the way. If you are noting down your notes, make sure that you note down this. Or you go through the question bank, you'll find it multiple times being asked. The chloride of sulfur is called disulfide dichloride. and is covalent liquid. So don't write it as a solid. So we are saying that sulfur, on heating it with chlorine gas, that's why we are saying the conditions are being mentioned. The conditions are being mentioned that heated sulfur, the condition is heated sulfur, and once it's heated, it is going to react with a dry gas, which is dry chlorine gas. So heated sulfur will always react with dry chlorine gas to form the disulfide dichloride. That will be a statement. Then you give us an equation for that, showing that sulfur as a solid reacts with chlorine as a gas to form disulfide dichloride. Always listen to these notes and you understand how each of the respective compounds is named. That's why I take long recording these videos. And note down as you are reading, for those of you who are already having the notes. So proceeding, we are saying that disulfide dichloride fumes in moist air due to hydrolysis by water. So most of the chlorides of PO3 elements hydrolyze in water, and we are saying that hydrolysis of disulfide dichloride in water is always going to yield as sulfurous acid, hydrochloric, hydrogen chloride gas, and sulfur. That means that the mixed fumes are always this hydrogen chloride gas, and this you may do it in your laboratory if at all you can prepare these compounds, which I don't think so in most of the schools in our country. So disulfide dichloride hydrolyzes in water to form sulfurous acid. This is sulfurous acid. It's not sulfuric. It's called sulfurous acid. Sulfurous acid. Yeah, and it will give off mixed fumes of hydrogen chloride gas. And lastly, we shall have yellow solids being formed. I said we avoid the word deposit. We don't have deposit in chemistry. Deposits are formed by magnets. So here we shall form most misty fumes, and those misty fumes are going to be for hydrogen chloride gas. And we shall form a yellow solid, which is going to be for sulfur. And then we shall form sulfurous acid as our aqueous solution. Now this one is colorless, it does not have a color. So in proceeding, we are going to look at the hydrolysis of PO3 chlorides. As I've already mentioned in the earlier video, that all the chlorides undergo hydrolysis. So what happens during the hydrolysis? So for ionic hydrides, they always undergo hydrolysis. That's a full topic in physical chemistry, and it will also be covered on this platform. So we are saying that sodium chloride dissociates in water to form neutral aqueous solution. Now the reason for this is because sodium chloride does not undergo hydrolysis. That's why it forms a neutral aqueous solution. For hydrolysis, just to give you a hint, I told you this is going to be a full topic in physical chemistry, and that video will still be uploaded on this channel. Sodium chloride in solution is going to ionize to give sodium ions and hydroxide ions, and chloride ions, and each of these ions reacts with the sodium ion reacts with hydroxide ion from hydrolysis of water to form sodium hydroxide, and chloride ion react with hydrogen ion still present in the solution. So you find that both of them, sodium is forming a strong base and chloride ion is forming a strong acid, which is HCl. So you find that they neutralize each other and the solution remains neutral. That's why, to simplify it, we say that sodium chloride forms a neutral solution because it does not undergo salt hydrolysis. Now let's look at other elements like aluminium chloride. If you look at aluminium chloride undergoes hydrolysis, and the reason for hydrolysis is due to high charge density. The higher the charge density, the higher the polarizing power. So the aluminium ion in aluminium chloride greatly polarizes the water molecules. So the higher the charge density, once the aluminium ion is having a charge density, is going to attract water molecules towards itself, like here in the first equation. And the high charge density is going to cause a high polarizing power. So it's the polarizing power caused by the high charge density that will bring about this equation. So part of the water molecules are going to be polarized to release a proton in solution. So this proton being released is the one which is responsible for making the solution in which aluminum chloride is in acidic, and we call that one salt hydrolysis. I've told this a full topic in physical chemistry. So don't worry, we shall cover that in details. So you're saying that hydrated ions undergo hydrolysis to release a proton in solution. And this proton is what causes the solution to be acidic. Proceeding, we're having aluminium chloride reacting with water. And this is a very common question. They ask you, how does aluminium chloride react with water? Or is aluminium chloride reacts with water to give us an hydroxide? And this is the simplest equation. So aluminium chloride reacts with 3 molecules of water to form aluminium hydroxide and 3 molecules of hydrogen chloride gas. So what do you expect to be the observation? We shall see mist white fumes that form these white fumes with concentrated ammonia solution. So they are these ones. Silicon chloride, we looked at it in group 4. Reacting it with water, it will always form silicon oxide and hydrogen chloride. We said all tetrachlorides of group 4 elements, when they are hydrolyzed in water, will form corresponding +4 oxides or dioxides with release of hydrogen chloride gas. Now we are saying both chlorides of sulfur or phosphorus hydrolyze in water to give us hydrogen chloride gas. Now I want you to notice that the elements that undergo reaction, the chlorides that undergo reaction with water, we are all forming hydrogen chloride gas. So never forget that. Hydrogen chloride gas is being formed in each and every reaction that is possible. So hydrogen chloride gas, never forget that product. With silicon tetrachloride, we shall form silicon oxide, and with phosphorus 5 chloride, we shall form phosphoric. This is called phosphoric, and this is called phosphorus. That's why we are saying we form acidic solutions. This is called phosphoric acid, phosphoric acid, and this is phosphoric. This is phosphoric, and this is phosphoric. So differentiate the two. What varies is the number of oxygen atoms attached to the phosphorus atom. So take note of that. Now let's proceed to the melting points of the chlorides. Now we say that sodium and magnesium chloride are going to be ionic, like in the table that we started with, and I gave that as an assignment. So I'm just going to be going through the statements briefly. We are saying that there's a progressive decrease in melting point from sodium chloride to aluminum chloride. And we are saying that for metals or for ionic compounds or for ionic chlorides, we look at polarizing power. We explain them in terms of polarizing. So all of them are having ionic structures, but what's going to vary them? We refer to polarizing power. The higher the charge on the cation, the higher is its polarizing power, and the greater it polarizes its corresponding anion. In this case, we are having a chloride ion. The weaker the ionic bonds holding it, and once the ionic bonds holding it get weaker, we expect a progressive decrease in melting point, because energy required to break such bonds will be low. And that's what all this paragraph is talking about. Now we are saying that melting point decreases from aluminum chloride to silicon chloride. Why is that the case? So you find that all other chlorides, I told you silicon tetrachlorides of group elements are all covalent. and all other chlorides of group PO3 elements, starting from silicon, they are going to have they are going to have simple molecular structures. And we say that simple molecular structures are always held by weak van der Waals forces of attraction. And in turn, van der Waals forces of attraction, their strength or magnitude is always dependent on the molecular size. That's why the larger ion in terms of molecular weight, you calculate their molecular mass the way you used to calculate them at A level. So you find that the one with the highest molecular weight or molecular mass is going to have the highest boiling or melting point. Reason being, the van der Waals forces are going to be stronger, implying that the forces holding its structure are going to require more energy to be broken. That means that they are going to have a progressive increase in melting points. Similarly, we are going to look at the oxides of the group's 3 elements, and we are going to look at the same concepts. Wherever we are going to explain these concepts is going to remain the same. That's why I'm just going to pass through the melting point part, because I've explained this numerous times. You talk about the structure. After talking about the structure, you talk about the forces holding that structure. After talking about the forces holding that structure, then you determine what's going to affect such forces. That's why we are saying that. That's why you're going to see that from sodium to aluminium oxide, all of these ones have giant ionic structures. By giant ionic structures, what determines them? You're going to find that giant ionic structures are affected by the product of charges. So we expect an increase. We are seeing an increase in melting point from sodium oxide to aluminium oxide. And why is that the case? Reason being, from sodium oxide to aluminium oxide, there are two reasons. First of all, we're having a decrease in ionic radius of the cations. The ionic radius is decreasing. That means that ionic bonds holding the giant ionic structures are going to be shorter. And once they are shorter, they are going to be stronger. Hence, they are going to require more energy to be broken. However, the other reason could be in terms of less energy. So you see that sodium and oxygen here we are having a positive 1 on sodium ion and positive 2 on oxygen ion. So the product of charges here is very low, it's going to be 2. But for magnesium, we are having a positive 2 on magnesium ion and similar applies to oxygen. So product of charges is going to be 4. So that means that magnesium oxide is having a higher melting point than sodium oxide because the product of charges in magnesium oxide is greater than that in sodium oxide. Going to aluminium, that's the same case. Aluminium is going to have a positive charge of +3. And oxygen is going to have 2. So 2 times 3 is giving 6. So aluminium oxide is having a higher melting point than magnesium oxide because the product of charges is higher in aluminium oxide than magnesium oxide. And the other reason is because the cationic radius in aluminium oxide is smaller than that in magnesium oxide. And that's what will determine the strength of the ionic bonds. So you talk about the structure, you talk about the forces holding the structure, and then you determine what affects the strength or magnitude of those structures. So you go to silicon oxide. Silicon has an independent structure, and you are saying that it has a giant covalent structure. You can this one is also acceptable, but you can change it to a giant covalent structure. In that, it's going to have very many short covalent bonds, the silicon to oxygen bonds. The silicon to oxygen bonds are going to be very many, and since it has a giant covalent structure, these very many strong short covalent, they are short and they are very many. They are going to be requiring a very high amount of energy to be broken, and once you require a very high amount of energy to be broken, that means that melting point is going to be higher than the rest of the elements. I think I've explained all of these ones. So we also talked about aluminum oxide being predominantly covalent. I said aluminum oxide can only be predominantly covalent because of polarization. Like if you had to compare the melting point of magnesium and aluminum, this one is 3000, this is 2000. So the reason for that, we expected aluminum to have a higher melting point than magnesium oxide. But however, that's not the case. Now, those abnormalities are brought about as a result of polarization, weakening the ionic bonds within aluminum oxide. And what causes that? It's always polarization. That's why we are saying that aluminum ion in aluminum oxide is having a higher charge density of +3. Hence, it is going to greatly polarize the anion attached to it, and the anion attached to it in that case is oxygen or oxide ion. So once it's going to polarize, ionic bonds are going to become very weak. And once they become weak, that means that energy required to break them is going to be low, and subsequently leading to a progressive decrease in melting points. So let's proceed. So in proceeding, we are saying that oxides of sulfur, phosphorus, sulfur, and chlorine have simple molecular structures. And I've explained this. I've told you and explained melting points. You first state the structure. After that, you talk about the forces holding the structure, and you talk about what determines their strength or magnitude. So simple molecular structure, the forces holding the simple molecular structures are always weak Van der Waals forces of attraction. And what affects their strength or magnitude? You always find that it's always going to be molecular mass. So the oxide of the compound with a larger molecular mass or molecular size or molecular weight is going to have it will be having stronger Van der Waals forces of attraction, and we expect it to have the highest melting point. However, the compound with the lowest molecular mass or molecular weight is going to have the weakest Van der Waals forces of attraction. That means that this structure is going to be weak, and thus is going to be easily overcome, leading to a lower melting point. Now let's look at how some of the oxides of sulfur are prepared, and these ones are prepared by heating oxygen. We have both in limited oxygen. In limited oxygen, we form phosphorus 3 oxide. Phosphorus 3 oxide is written in this form and is white in color. Phosphorus 3 oxide, however, is ionic. So ionic, when dissolved in water, we form phosphoric acid. I told you this is phosphoric acid, and the other one is phosphoric. So phosphorus 3 oxide, when dissolved in water, we form phosphoric acid. Take note and be aware about that. So in proceeding, we are saying that phosphorus trioxide is acidic, therefore reacts with alkalis such as sodium hydroxide to form disodium hydrogen phosphate. Now this is a very important equation. You should bold it or note it somewhere. Say that whenever you are coming to read these equations, you read it first, because we usually ask it, though it's not commonly asked in UNEB, but you may not survive it in mocks. So take note of this equation and always practice them to master them. So proceeding to phosphorus pentoxide, this is prepared by heating phosphorus in excess supply of oxygen. So when you're having excess supply of oxygen and we heat phosphorus in it, I told you conditions are very important when you are writing your equations. This equation is not possible if there was no heating. So to prepare phosphorus pentoxide, we always heat phosphorus, which always exists as tetraatomic, as already explained earlier on. So phosphorus oxide is heated with oxygen to form phosphorus pentaoxide. This is phosphorus pentoxide. Now we are saying that the acid is acidic, so it reacts with water to form phosphoric. Now this is not phosphoric. This was supposed to be phosphoric. So change this E, let me highlight it. Change this O to E. This was supposed to be E. to form phosphoric. Phosphoric is the one which has 4 here. So this is called phosphoric acid. When phosphorus pentoxide reacts with water, it will form phosphoric acid. However, if it reacts with sodium hydroxide, it will form sodium phosphate and water. Let me hope you cover this in your O level. So let's proceed to the next slide. And in this video, we are going to look at how sulfur dioxide is prepared. Now, this is a very common question in UNEB, especially paper 1. And there's a full topic about it is covered in physical chemistry. But briefly, I summarized it here also in inorganic chemistry. Now, in the industrial scale, we prepare sulfur dioxide. Now, sulfur dioxide is a raw material in preparation of sulfur trioxide. But let's first look at how sulfur dioxide can be prepared. Sulfur dioxide can be prepared by simply heating sulfur in presence of oxygen to form sulfur dioxide. And once you dissolve sulfur dioxide in water, you are going to get sulfurous acid. Sulfurous. However, when you heat sulfur in excess oxygen, you are going to form sulfur dioxide, and this sulfur dioxide gas being formed will react with excess oxygen to form sulfur trioxide gas, which is the equation here. But however, let's first look at this. So we are saying that if you react sulfur dioxide gas with alkalis, especially sodium hydroxide, it's going to react. The reason why it's reacting is because sulfur dioxide is an acidic gas. So being an acidic gas, it reacts with alkalis to form sodium sulfate or to form a sulfite ion and water. Let me hope this is very simple to understand. So take those notes and make sure that you master them properly. Make sure that your states are well written because poor handwriting and ignoring states may lead to loss of marks. So proceeding, we are saying that let's look at sulfur trioxide. Now this is the very commonly set in paper 1. You should take note about this. The good news is that we have a full topic and we shall look at it individually, in depth of how it's being prepared and how you can approach its questions. So to prepare sulfur dioxide, we heat sulfur dioxide. To prepare sulfur trioxide, we heat its sulfur dioxide gas in excess oxygen. But conditions must be present, which is vanadium 5 oxide, and heating must be required. So when you're setting this question, you ask you for what raw materials can we use to prepare sulfur dioxide, and you tell us that we need sulfur dioxide and oxygen. And then we shall ask you what are the conditions for that reaction. You tell us that we need vanadium pentaoxide as a catalyst, and you tell us that we shall need heating. So be aware about this equation. The arrow showing information of products must be reversible because this falls under chemical equilibrium and it must be covered under chemical equilibrium. Arrow must be reversible, showing that this reaction is carried out on conditions. Like such reactions are carried out in reaction vessels. An arrow can't be straight. You are going to look more in depth about this in chemical equilibrium. That's when you enjoy the art of physical chemistry. So proceeding, we are saying that sulfur trioxide is acidic, hence reacts with water to form sulfuric acid. Many of that was covered in O level. Sulfur trioxide also reacts with sodium hydroxide to form sulfate ions and water. So let's proceed. Always make sure that you have your notes well organized. Now looking at the period 3 hydrides. Hydrides for metals, when hydrogen combines with metals we form ionic hydrides, and I told you that bonding is going to be either ionic or covalent. So structure, that means that you're going to have giant ionic structures and simple molecular structures. Let me hope you can describe their melting points. for things that have simple molecular structures and for things that have giant ionic structures. We have looked at a lot of examples, and we shall look at more examples under the video that will be uploaded about group 4 elements, so that melting points becomes a compulsory or sure number for every one of you. So you are saying that sodium hydride is prepared by heating sodium in hydrogen gas to form sodium hydride, and the hydride is ionic, therefore it dissolves in water to form sodium hydroxide and hydrogen gas. Similar applies to magnesium. Magnesium, to prepare it, you need to heat magnesium in dry hydrogen gas. I told you, when you say heating, you have to write dry, because when you're heating, that means that the gas you're heating it with is going to be dry. So magnesium reacts with dry hydrogen gas to form magnesium hydride. And we say that it's also ionic, therefore it dissolves in water to give us an hydroxide plus hydrogen gas. So take note of that. So now let's look at aluminium hydride. Now this one is a bit complex and is likely set by most people because it's not prepared the same way like the other hydrides. Let's look at the next slide. So we are saying that aluminium chloride can be prepared when you react it with lithium aluminium tetrahydride. When you react aluminium chloride with lithium aluminium tetrahydride in presence of ether, you are going to get the chloride of aluminium you are looking for. So that's how you can prepare. Now this equation was not written properly. Yeah, I think it was written properly. Make sure that you write the symbols properly. So we are saying that aluminium hydride reacts with water to give hydrogen gas and aluminium hydroxide solution, which is slightly soluble in water. Aluminium hydroxide, we have already looked at it in our O-level practicals, forming a white precipitate dissolving in excess. That means that aluminium hydroxide is insoluble. However, when we add water to the hydride of aluminium, we always have a tendency of forming an hydroxide, and the state must be a solid because amphoteric hydroxides are always solids in nature. So let's look at selene. Selene is another name for silicon 4 hydride. Selene is also prepared in the same way, but we don't need presence of ether. So you heat selene with lithium aluminium tetrahydride, forming what you want, which is silicon 4 hydride. You can also call it silicon hydride. You also form lithium 1 chloride and aluminium chloride. We are seeing that this is how selene reacts with sodium hydroxide. Now you should note this equation because it's very important and we ask for it. This equation here. I want you to note down that under group 4 elements, it's only silicon 4 hydride. Other hydrides do not react with sodium hydroxide. So it's only selene or silicon 4 hydride that reacts with sodium hydroxide in presence of water to form a complex, which is sodium silicate and hydrogen gas. So be aware of this equation and take note about it. Other hydrides of group 4 do not, but other elements, compounds of or hydrides of pure crude can react with sodium hydroxide. So let's look at another preparing phosphine. Phosphine, we have already looked at it in this equation. I've already talked about this equation and I've already told you to note it somewhere. So you are seeing it's repeating. So phosphine is this gas here, pH3. We call it phosphine gas. We describe this one as sodium dihydrogen phosphonate. So make sure that you know their chemical names. So phosphine can also be prepared by reacting calcium phosphide with water. We shall form the calcium hydroxide plus the phosphine gas we need. Hydroxides of calcium are always aqueous, that's why I'm putting here aqueous, and phosphine is a gas in nature. Phosphine is a gas, that's why we are giving it a state of a gas. So be aware of your states as you are taking your notes. Or you can review notes and see which states you give to them, because states can lead to loss of marks. Let's look at another sulfide. Here we are going to look at hydrogen sulfide. Now, mock bodies like to ask this question because it confuses students. Hydrogen sulfide is prepared by reacting iron to sulfide. Not iron 3, but iron to sulfide. We react it with hydrogen chloride or hydrochloric acid to form iron to chloride. That's how we prepare iron to chloride. That's how we prepare this hydrogen sulfide gas. So take note of this equation. It came in Waukesha, I think it was 2023. They were being asked this question. I think it may reflect back in UNEB in any of the current years. So iron to sulfide reacts with dilute hydrochloric acid to form iron to chloride and hydrogen sulfide gas. So kindly be aware and take note of that. Now, approaching the other question, we are saying that hydrogen sulfide is covalent and is slightly soluble in water, thus it forms a weak acid. Now, we are going to look at this also in hydrolysis, salt hydrolysis. These things that are ionized in water to form acidic solutions, we always react them with other elements. These protons always react with other elements. Like if hydrogen sulfide is mixed in water and added to a solution containing sodium carbonate, the protons which are being released, like these ones, always react with the carbonate ions to form carbon dioxide gas. But however, that will be looked more in depth in the physical chemistry topic. So let's proceed to the next slide. Proceeding to hydrogen chloride, this can be prepared by reacting a metal chloride with concentrated sulfuric acid. As you are seeing sodium chloride, when you react sodium chloride with concentrated sulfuric acid, you are going to form sodium hydrogen sulfate with hydrogen chloride gas. Now, as earlier as I stated in the earlier video, I said if sulfuric acid is dilute, we shall form sodium sulfate. However, for concentrated sulfuric acid, we always form sodium hydrogen sulfate. So take note and be aware about that. That's why we are saying that if you are going to react sodium chloride with hot concentrated sulfuric acid, you are going to have sodium hydrogen sulfate plus hydrogen chloride gas. And then we are saying that hydrogen chloride is covalent and is thus fairly soluble in water to form an acidic solution. Hydrogen chloride gas reacting with water is going to give us hydroxonium ion. I say this is called an hydroxonium ion. If you have forgotten it, rewrite it again. This is called hydroxonium. It's called an hydroxonium ion plus the chloride ion. So always remember that and never forget. And this brings us to the end of our video. It has been compiled and brought to you by Wagembe Yusuf. To reach me out or to having any queries or any consultation or mind map about chemistry or mathematics, my contact details are provided you are serious. So I meet in the next upload. Subscribe, share the video to your friends so that you can all benefit as a family. So see you in the next video.